Okay. So, dear ladies and gentlemen, I'm Xiaolong Li from I'm a master student from Zhejiang University. Our work is a joint fabrication of large-scale interactive objects assembled by 3D printed conductive parts with copper plate joints. So, I'm very excited to share with you our work and the interesting findings in the process. So our aim is to assist personal makers in using consumer-grade 3D printers to fabricate large-scale interactive objects, which our session is about big to small fabs. This is big one, but I will expand. So the large scale is relatively large. So it includes two parts. The first one is 3D printed conductive parts, and the second one is copper plated joints. So what does that mean? I'm gonna explain that, but later. Personal fabrication is of interactive objects is very interesting field. To achieve the interactive objects, the most critical step is to make the circuits. So, and there is many ways, maybe tons of ways to doing this. It's both interesting, but such as like spraying, printing, and cutting. However, this is limited to the flat surface or manually attaching them to the outer surface of objects. And to achieve more diverse circuits, it's maybe necessary to rely on 3D printing or even 4D printing or processing in shape, such as the heat bending. So using the 3D printer, we can easier to fabricate more complex and more interesting circuits in the structures. So, of course, the key is what's the problem, what's difficult are we facing. For our goal is that build large-scale interactive objects. This large is meant we compare to the method we use. The first problem is there are limitations in the printing forming area. So currently the forming size of most common printer we can see on the markets is limited to the forming area is limited to 25 plus times 25 centimeters. Secondly, the equipment, there has the commercial equipment can currently perform integrated circuit making, but it's often expensive and is not suited for rapid or large manufacturing. Finally, the currently available conductive 3D filaments have the limitations in conductivity, in price, and the printing performance. For those expensive filaments with high conductivity, they are not easy to print, while the cheap materials that isn't that conductive. So what is our design principles? Our idea is about it's actually quite simple. That is, first we don't want to looking for complicated or expensive equipment or materials. They has to be accessible. The second, we want to put those difficulties and challenges at the front in the design stage and the machine manufacturing stage, and only leave the simple and error-free manual steps. So specifically, we achieve this. First, we achieve the segmented manufacturing of components through the electrified joints structures, and then we electroplate and enhance the already made the low performance circuits. So this is the basic structure of each joint. It's presented here. As shown in the figure, the parts of the interactive objects are first manufactured in segments. Like the component X and the component Y, they're separately to manufacture. That's why we can use every single each of our platform, our printing bed. So after completing the the printing and the copper plating, and we insert those components, electrical components, to make this object work, right? And then we finally plunge through the joints to complete the connection between the parts, and then we make the final product. So here, C1 shows another feature, an interesting feature about eJoint is it can conduct internal circuits. There is not only we built not only the circuit structure itself, but we also built the cavity structures corresponding to and folding to the circuits. So the solution we use, the copper plating solution, goes into the object and gets the internal circuits copper plated. So I will to introduce our fiber pipeline. Okay, the user first needs to decide where they cut, because they're large objects we want to cut and build. So there decides the cutting position, then the layout of the circuits, and the placement of the components can be completed through the Grasshopper plugin. As we mentioned before, the user can not only set those tracks, those circuits on the surface, but also the inside of our object. The conductive PLA we use is with 15% of carbon nanotubes was dropped into the common PLA, but then it can be conductive. Although this material has poor conductivity, but it's cheap, and what's most importantly is the same printing parameters to the common PLA we use. So we can print these two materials together, and we can put it relatively faster. We can support up to 200 of millimeters per second speed. So that's quite fast, actually. So the third step is to soak the interior part and electroplating the solution with the copper ions. By applying a direct current to the conductive PLA, the conductive part, we can get a thin layer of copper on the circuit. So we get, before we printed a low performance circuit, but we reinforced it with copper. But now it can be conductive. So the first step is to cut off the clipping pads and install the electronic components like this, and we can finish the parts, the segments. The final step is we plunge to each other to complete the overall manufacturing procedure of the object. So furthermore, for the different scenarios, we have designed 4 different kinds of joint structures which can achieve connections in vertically and horizontal directions. Although the original intention of the idea we come with, the traditional motorized antenna structures, should be strong and non-detachable structure, right? But we still designed a spring joints that can be repeatable, plunging to meet the maybe modularization needs, like this. Oh yeah, it just passed. So, okay, so this is 4 kinds of joints, the E-joints. Then we want to know how capable our methods and where is the boundary lies. So we conduct an overall evaluation of the electronical and the mechanical properties of eJoint. We tested the minimum line width that eJoint can support, and the appropriate cross-sectional area range of the conductive trace during the printing, because this is critical because you don't want the resistance is too high. Then we believe that the trace we use can be usable when the resistance drops below 0.05 ohms. Therefore, we recommend the traces with width more than 3 millimeters. We tested the appropriate cross-sectional area size of the cavity. The cavity I mentioned is built to the internal circuits. So when electroplating with the silt bore cavity, the solution can go in and make appropriate copper plating. For the capacity of our circuits, we continuously to torture them, actually, increase the power until the circuits burned out. In the case of 5.2 millimeters line width of the circuits we manufactured, it did not burn out until the current of 24.3 amps passed through. This is relatively not common we can see in this field. So this means that the single line can support as maximum power of 46 watts, which can maybe support most of the scenarios and applications. So we tested the maximum lines and can be copper plated within the 10 hours. So we don't want that too long of copper plating time, right? So the longest electroplating length we reached 45 centimeters, which is twice the side length of the printer's forming platform. So finally, we test the mechanical properties like the strands, how it's tough. So, and finally, we proposed several applications that shows the agent's ability. This is a desk set including a lamp, a fan, a wireless charging. You can use that to directly charge your phone. And this is a posture chair that can detect sitting posture. When in the normal use, the light will go always on. Yeah, but when you're sitting, it's just right. It will flash to as a reminder. So that is I'm going to talk about is the biggest for now we made is chaired, so they're large. Now finally, as we demonstrated in our fab process, is electronic instruments that can achieve the sound both the ukulele and violin. So just like many other workers, our method also had limitations. First, a joint is a connection method based on physical locking. Its connectionability not just limited by its structure, it's critical, but not just that, but also greatly restricted by materials. We found that although PLA is good, it's cheap, it's easy to print, it's fast, but the texture is relatively soft. So when the two segments is plugged to each other, it's strong. But when multiple sections or parts are connected in series, like the chair, right? It may be it increase the risk of failure. It has a risk. So in the future, we want to try material with stronger performance, such as ABS or the carbon fiber reinforced PLA. It will become for testing. So secondly, for the circuits, the copper plating traces. When the traces is too thin or too long, as I mentioned, it can be difficult to electroplate it. So, however, we found that the conductive PLA can be connected in parallel inside the objects and to drop the resistance of the whole part, the black part, the conductive part. Due to the significant difference in conductivity between the material we use and the copper layer, it will not be affected by the short circuit cost during the use. So finally, regarding our goal is to make large, right? Our application, the chair is the largest one. Its modeling volume far extends the volume that's the 3D printer we used, which is more than 8 times of it. But for the future, we want to make something bigger, like not just human scale, but vehicle, but maybe architecture. And then the printing speed, for now, is usable. But for them, the printing speed and the material cost may become a limitation. So in the future, we can solve this problem by replacing the non-core parts, the unconnecting parts with other materials. So finally, please allow me to repeat our contributions of this paper. So firstly, we provide a usable method for individual makers to manufacture large interactive objects. Secondly, we provide software, the plugin tools to help users in manufacturing. Finally, we conducted a series of the tests in the method, provide the specific parameters and explore the capability boundaries of our work. So this is all about our work, and thank you so much for your time. In addition, and I and my co-author Xu Yuefeng are currently seeking for opportunities for PhD. So thank you again, and looking for any questions. Yeah.
Maybe we can give time for one quick question if you have anyone. All right.
Hi, Lian Wu from Florida State. Good work. So I just wondering, have you thought about the connection to the resistor, Arduino board, or like other cable?
Okay. You mean, have we ever tested it with the baseline method, with the traditional way we use, right?
No, I was asking, so right now, I saw you put like the resistor Arduino board on LED, right? But you didn't use this kind of approach to connect to the electronic component, right?
Oh yeah. That is the really good questions. We would only test the segments and segments. What are these resistance? But we didn't mention about the. But I can show you these slides. Okay. So it's about our basic structures. So actually, we did some not that accurately test for the manufacturer process, because we need to like there. Sorry, I want to show you this. So we can see those parts that attached or connect to the electronic components, right? Yeah. They are also copper plated, but yeah, we didn't conduct that evaluation of this. But in the manufacturing process, we didn't find the connection problem yet between the components and our printing part. So that would be interesting. We will maybe in the future work well to fill these gaps.
Okay, thanks.
Thank you.
You're always welcome to talk to Xiaolong after the talk session. We have a post session over there.